Hello students, welcome to this new video lecture on Kinetic Theory Part 2. In the previous section, we have studied about molecular nature of matter, behavior of gases, and kinetic theory of an ideal gas. In this session, we will study about law of equipartition of energy, specific heat capacity, mean free path, and in the end we will answer some of the important questions of Mark 1 and Mark 2. So let us start. The root mean squared speed VRMS gives a general idea of molecular speeds in a gas at a given temperature. But we want to know more. In the year 1852, Scottish physicist James Clerk Maxwell first solved the problem of finding the speed of distribution of gas molecules. His result is known as Maxwell's speed distribution law, and its plot V versus speed versus the probability function is shown on the screen. In a given mass of gas, the velocities of all molecules are not the same. Even when bulk parameters like pressure, volume, and temperature are fixed, collisions change the direction and speed of the molecules. However, in a state of equilibrium, the distribution of speed is constant or fixed. Molecular speed distribution is very important and useful when dealing with the systems containing large number of objects like molecules in a container. The number of molecules between speeds v and v plus delta v, that is in a small strip around speed v, is shown on the screen. So the distribution formula is given by the relationship equation dn of v is equal to 4 pi capital N into m divided by 2 pi rt to the power of 3 by 2 into e to the power of minus m by 2 rt v square into v square dv, that is equal to nv dv. So this is the relationship. Here dn of v is the probability distribution function, because Maxwell used the probability theory to calculate the distribution, to calculate the speed. That is, dn of v is the number of molecules in the range delta v as shown in the figure. Please see the figure here. Delta v anywhere across the graph you can take the distribution dv, and n is the total number of molecules, capital M is the molar mass of the gas, and T is the temperature, absolute temperature of the gas. This is called Maxwell distribution, that is equation 1 is called the Maxwell's distribution function. The plot of number of molecules against speed is shown in the figure. The fraction of molecules with speeds v plus delta v is equal to the area of the strip. This is the strip, area of the strip considered. The average of any quantity like v square is defined by the integral of v square, that is equal to 1 by n integral v square dn of v, that is equal to square root of 3 kb into T by m, which agrees with the result derived from more elementary considerations. The three measures of distribution of speeds among the molecules are average speed, root mean square speed, and most probable speeds. These were shown in the Maxwell distribution probability curve in the previous slide, and it is reproduced again here. Please see here, the root mean square is the gray curve, is the highest of all the three, and the next highest is the average V average, and the speed corresponding to the peak is the most probable speed. So root mean square speed can be expressed as square root of 3p by rho. Vrms is equal to square root of 3p by r, where p is the pressure and rho is the density. It can also be expressed by other variables like, that is, Vrms is equal to square root of 3 into r into t divided by m, where m is the molecular weight of the gas. And similarly, another form of this relationship is Vrms is equal to square root of 3k into T by m, where small m is the mass of the molecule and K is the constant and T is the absolute temperature. The next important speed in the measures of the distribution of speed is most probable speed. It is the speed which is possessed by maximum number of molecules in a gas. So here you please see the curve. Here the maximum number of molecules are at this peak and the speed corresponding to it is Vp, that is probable speed, most probable speed. And this is given by the relation Vmp. V subscript Mp. Mp is most probable is equal to square root of 2p by rho, that can be expressed as also as square root of 2rt divided by m, and that is also equal to 2kt divided by m. See the difference here. We are using 2rt in the numerator, whereas in RMS we are using, it is in the formula is 3rt. All other parameters being the same. And there is another speed called average speed. It is the arithmetic mean of speeds of the molecules of a gas at a given temperature. It is the highest of all the other two speeds. And it is given by the relationship average V bar is equal to V1 plus V2 plus V3 plus etc. Vn divided by n. And its other forms are V average is equal to square root of 8p divided by pi into rho, that is also equal to square root of 8rt divided by pi into m, and that is also equal to 8 into kt pi into m. You please see the number inside the root. It is for average it is 8 and for mp it is 2 and for RMS it is 3. So you have to remember that Vrms is highest. That is Vrms greater than V average greater than Vmp. So for remembering trick, you can remember the word RAM. That is R for RMS is highest, next highest is average and next lowest is MP. Now we will also we will recall the formula for the kinetic energy of the gas molecule. So kinetic energy of the gas molecule is represented by the symbol E molecule is equal to half mv square. That is the basic formula. Here V is RMS V, well RMS speed. That is equal to half into m into 3 kt divided by m. That is simply square root of, that is the square of the formula given in the previous presentation. That is equal to 3 by 2 kt. Similarly, the kinetic energy of 1 mole, that is m gram of a gas, that is E mole is equal to half into capital M Vrms square, that is equal to half m into 3 RT divided by m equals 3 by 2 RT. Finally, the kinetic energy of 1 gram of gas, that is E gram, is equal to 3 RT divided by 2m equal to 3k into Na, that is Avogadro number, into T divided by 2m into Na, that is equal to 3k by 2m into T, that is equal to 3 by 2 gamma T. Please note that the molecule of ideal gas possesses only translational motion. So they possess only translational kinetic energy. In these equations, small m is the molecule mass of each molecule, capital M is the molecular weight of gas, and Na is the Avogadro number. That is equal to 6.03 into 10 to the power of 23. Law of equipartition of energy. As you know that there are different models of gases like monatomic, diatomic and triatomic, polyatomic, etc. From such models, we would assume that all the three types of molecules can have translational motions as well as rotational motions, and in addition we would assume that the diatomic and polyatomic molecules can have oscillatory motions, that is vibrations, with atoms oscillating slightly towards and away from one another as if attached to opposite ends of the spring. To keep account of various ways in which energy can be stored in a gas, James Clerk Maxwell introduced the theorem of equipartition of energy, which states that for any system in thermal equilibrium, the total energy is equally distributed among its degree of freedom, and the energy associated with each molecule of the system per degree of freedom of the system is half kT. Please remember, the energy associated with each molecule of the system per degree of freedom is half kT. Each translational and rotational degree of freedom constitute half kT to the energy. Each vibrational frequency contributes 2 into half kT, that is equal to kT energy. Since vibration has both kinetic and potential energy. For a monatomic of a single molecule, the kinetic energy is given by E is equal to half mvx square plus half mvy square plus half mvz square, that is equal to half plus half plus half, that is equal to 3 by 2 kb, where kb is the Boltzmann constant. Let it be equation 1. For diatomic, kinetic energy of a single molecule is both, it has got both translational plus rotational. Therefore, E is equal to Et plus Er. So, that is given by the formula E is equal to half mvx square plus half mvy square plus half mvz square plus half I1 omega 1 square plus half I2 omega 2 square. Please note that I1 and omega 1 and I2 and omega 2 are related, associated with the rotational motion. Therefore, here omega 1 is the and omega 2 are angular frequencies. Summing up, half plus half plus half plus half plus half, that is 5 times 5 by 2 into kb into T. Let it be equation 2. Here we assume that molecule does not have vibrations. If vibrational mode is considered, then for diatomic molecule, then vibrational term is given by the expression E is equal to half into m into dy by dt whole square, and therefore the total energy is E is equal to E translation plus E rotation plus E vibration. Let it be equation 3. Degree of freedom. Degree of freedom is used extensively in determining the kinetic energy of the molecule by applying equipartition of energy. As you know, every kind of molecule has a certain number of degrees of freedom, which are independent ways in which a molecule can store energy. The molecules will in general have velocity components along three axes. Thus, gas molecules of all types have 3 degrees of translational freedom, 3 ways to move in translation, and on average the associated energy of 3 into half kT per molecule. Let us find the expression for degree of freedom. The total number of independent modes in which a system can possess energy is called the degree of freedom and represented by the letter small f. The degree of freedom are of three types: translational degree of freedom, rotational degree of freedom, and vibrational degree of freedom. General expression for the degree of freedom is given by the relation F is equal to 3n minus r, where small f letter is the degree of freedom, n is the number of independent particles, and r is the number of independent restrictions. For a monatomic gas, it can have 3 degrees of freedom, that is all three translational. The diatomic gas has 5 degrees of freedom, that is 3 translational and 2 rotational. And the third one is triatomic gas, that is nonlinear. It has 6 degrees of freedom, 3 translational and 3 rotational. At high temperatures, the molecule will have an additional degree of freedom due to vibrational motions. The table below shows the relationship between the atomicity of a gas and the kinetic energy, and it also shows the figure. For example, please see the figure here, the table on the right hand side of your screen. For a monoatomic gas like helium, the number of independent particle is 1, because helium has only one atom, so independent particle is 1, and there is no restriction, independent restriction, that is r is equal to 0. Therefore F is equal to 3n. It becomes F is equal to 3. Therefore, this figure, the single atom is shown here, and its kinetic energy becomes 3 into half kb into T. Half kb into T is given by equipartition theorem. Similarly, we can calculate for diatomic gases like hydrogen, which has n equal to 2, r is equal to 1, and F is equal to 3n minus r. It becomes F is equal to 5, and the independent restriction is also shown. The distribution is linear here. It is shown. So, because F is equal to 5, the kinetic energy is 5 into half kb into T. Similarly, you can examine for triatomic non-linear and triatomic linear, where the figures are shown as the distribution, which will have different r, that is in 3 and 2 respectively, and the inner energies are given by 3 kbt and 7 by 2 kb into T respectively. Specific heat capacity. We have studied about specific heat capacity in chapter number 11, that is thermal properties of matter, as well as in chapter number 12, thermodynamics. Here we are just extending our analysis of molar specific heats to ideal diatomic and polyatomic gases. It is necessary to retrace the derivations of that analysis in detail. Let us examine. The gram specific heat, which is defined as the amount of heat required to raise the temperature of unit gram mass of the substance by unit degree, is given by the relation small c is equal to delta Q by m into delta T, where delta Q is the heat transferred and delta T is the change in temperature. M is the mass of the molecules. Molar specific heat. It is defined as the amount of heat required to raise the temperature of 1 gram mole. Please note 1 gram mole, that is mu is the mu of the substance by a unit degree. It is represented by the letter capital C. Therefore, its definition is capital C is equal to delta Q divided by mu. Please note here mu into delta T. In the previous gram specific, it was small m. Here it is mu, that is mole. Therefore, C is equal to, substituting mu as small m by capital M, we get C is equal to m into C, capital M into C. Specific heat of gases. In adiabatic process, delta Q is equal to 0. That is, the heat transferred is 0. Therefore, when we put the value of delta Q equal to 0 in equation 1, we get C is equal to 0. Therefore, in adiabatic process, the molar specific heat is 0. Similarly, in isothermal process, as you know, the change in temperature is zero. That is, the iso means same, thermal means same temperature. So there is no change in temperature. Therefore, delta T is equal to 0 and capital C is given by the relation delta Q by M into delta T. Because delta T is 0, denominator is 0, C becomes infinity. Therefore, C has got a wide range of positive values ranging from 0 to infinity. Further, it can even be negative. Out of many values of specific heat of gas, two are very special significance. The specific heat of gas at constant volume, as we have seen, it is defined as the quantity of heat required to raise the temperature of unit mass of gas through 1 Kelvin when its volume is kept constant. That is, C subscript V is that V is the constant volume. Therefore, specific heat of a gas at constant pressure Cp. So, subscript P is the for constant pressure, which is defined as the quantity of heat required to raise the temperature of unit mass of gas through 1 Kelvin when its pressure is kept constant. Therefore, Mayer's formula states that Cp minus Cv is equal to R. Please note that Cp is always greater than Cv. Hence, Cp minus Cv is equal to R. This is the relation and is called Mayer's formula. And it shows that Cp is always greater than Cv. That is, molar specific heat at constant pressure is greater than that at the constant volume. Now let us compare the specific heat of specific heat capacities for different gases. Table 1 shows the predicted values of specific heat capacity of gases. Here we are ignoring the vibrational modes. So therefore, we will first consider nature of gases. And for a monatomic gas, Cv that is expressed as joules per kg per Kelvin, the value is 12.5. And for monatomic gas, Cp, the value of Cp in joules per mole per Kelvin is 20.8. Therefore, Cp minus Cv is 20.8 minus 12.5 equal to 8.31. Similarly, we can calculate the value of gamma. Gamma is equal to Cp by Cv. That is, Cp is 20.8 divided by 12.5. For diatomic, Cp is 20.8, Cv is 20.8, Cp is 29.1, Cp minus Cv is again 8.31 and gamma value Cp by Cv is 1.4. The triatomic gases, the Cv value of Cv is 24.93 and Cp is 33.4 and Cp minus Cv is 8.31. Gamma is 1.33. Again, that was the predicted value. The table 1 showed the predicted value for nature of gases. Again, we can actually measure values by conducting experiments. The specific capacity of gases is shown in table number 2. So, the nature of monatomic gas like helium has Cp 20.8 and Cv 12.5, Cp minus Cv is 8.3 and gamma value is 1.66. Similarly, you can see the values and note down. Pause the video and note down for diatomic, triatomic and polyatomic gases like hydrogen, nitrogen, oxygen, H2O and methane CH4. All these values are shown in the table. Mean free path. Molecules in a gas have rather large speeds of the order of the speed of sound. Yet a gas leaking from a cylinder in a kitchen takes considerable time to diffuse to the other corners of the room. Similarly, the top of a cloud of smoke holds together for hours. This happens because molecules in a gas have finite, though small size. So they are bound to undergo collisions. As a result, they cannot move straight unhindered. Their path keeps getting incessantly deflected. So let us study about the mean free path. The average distance traveled by a gas molecule is known as the mean free path. And mean free path is represented by a symbol lambda. In the NCERT textbook, he is using the letter L, but it is better to represent it by Greek letter lambda. That is equal to the average distance, that is velocity. Average velocity is v bar into tau, where tau is the time taken and v bar is the average velocity. So considering and imagining the volume swept by a molecule in delta time to collide as spheres, we get lambda is equal to v bar tau, that is equal to n pi into d square. This is, we have assumed that the other molecules are at rest. Only this example is moving. So here the letter D represents the diameter of the molecule in the shape of a sphere. Considering the motion of all other molecules, previously we considered that all molecules are rest except the molecule under consideration. Now considering the motion of all the molecules and substituting the value of average velocity, average speed by Vrms, root mean square, we get lambda is equal to 1 over root 2 into n pi d square. So if we take the single molecule and average velocity, it is 1 over n pi d square, whereas RMS value, if we consider, lambda will be equal to 1 over root 2 into n pi into d square. So let lambda 1, lambda 2, lambda 3, etc. up to the lambda n be the distance traveled by gas molecule during n collisions. So there are a number of collisions, hence the distances traveled by the gas molecule changes. Then the mean free path of a gas molecule is given by lambda is equal to lambda 1 plus lambda 2 plus lambda 3 plus etc. 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 up to lambda n divided by n, where n is the number of molecules. That is, therefore lambda 1 is equal to 1 over square root of 2 into pi into n into d square. D is the diameter, n is the number of molecules per unit volume. Let us consider an example to calculate the parameters in respect of air molecules. So we know that the velocity, average velocity or average speed is 485 meters per second at STP, that is standard temperature and pressure. N is equal to 2.7 into 10 to the power of 5 per meter cube. Assuming D, the diameter of the molecule, to be 2 into 10 to the power of minus 10 meters, we get the time taken as 6.1 into 10 to the power of minus 10 seconds. And we can calculate the mean free path as 2.9 into 10 to the power of minus 7 meters. That is approximately equal to 1500 D. Now we have completed the theoretical part of kinetic theory. Now we'll take up some examples. Question 1. The density of water is 1000 kilograms per meter cube. The density of water vapor at 100 degrees centigrade Celsius and 1 atmosphere pressure is 0.6 kg per meter cube. The volume of molecule multiplied by the total number gives what is called the molecular volume. Estimate the ratio or fraction of the molecular volume to the total volume occupied by the water vapor under the above conditions of temperature and pressure. Answer. For a given mass of water molecules, the density is less if volume is large. Therefore, so the volume of the vapor is 1000 given parameter divided by 0.6. Therefore, that is equal to 1 over 6 into 10 to the power of 4 times larger. If the densities of the bulk water and water molecules are same, then the fraction of molecular volume to the total volume in liquid state is 1. As volume in vapor state has increased, the fractional volume is less by the same amount, that is 6 into 10 to the power of minus 4. Next question. Estimate the volume of a water molecule using the data in question 1. That is, given data parameters you have to assume in question number 2, but here you have to estimate the volume of water molecule. Answer. The density of water molecule is approximately equal to density of bulk water, that is equal to 1000 kg per meter cube. Therefore, 1 mole of water has mass approximately is equal to 2 plus 16 grams. That is equal to 18 grams. That is the standard value. 1 mole of water has a mass of 18 grams. That you have to remember. Therefore, that is equal to 0.018 kg. That is converting grams into kgs. Therefore, since 1 mole contains 6 into 10 to the power of 23 molecules, that is Avogadro number, the mass of molecule of water is m divided by Na, that is equal to 0.018 divided by 6 into 10 to the power of 23 kg. That is equal to 3 into 10 to the power of minus 26 kilograms. Therefore, volume of water is mass divided by the volume. That is equal to volume is equal to mass divided by the density. 3 into 10 to the power of minus 26 kg divided by 1000 kg per meter cube. This value, denominator value, is given in question number 1. Please read the question number 1 and substitute the value. 3 into 10 to the power of minus 6 kg is calculated in the previous step. Therefore, that is 3 into 10 to the power of minus 29 meter cube. That is equal to 4 by 3 pi into radius whole cube. Now we have to calculate the radius. Hence, radius is equal to approximately, from these readings, we can calculate radius equal to 2 into 10 to the power of minus 10 meters. That is 2 angstroms. Next question. What is the average distance between atoms, interatomic distance in water? Use the data given in question 1 and question 2 in the previous slide. Answer. A given mass of water in vapor state has 1.67 into 10 to the power of 3 times the volume of the same mass of water in liquid state. So, the mass is more in the vapor state. this is also increase in the amount of volume available for each molecule of the water. When the volume increases by 10 to the power of 3 times, the radius increases by v to the power of 1 by 3 or 10 times. That is 10 into 2 angstroms. That is equal to 20 angstroms. So the average distance is 2 into 20, that is 40 angstroms. Next question. A vessel contains two non-reactive gases, neon, that is monatomic, and oxygen, diatomic. The ratio of their partial pressure is 3:2. Estimate the ratio of 1. Number of molecules. Part 2. Mass density of neon and oxygen in the vessel. Also calculate I assume that atomic mass of neon is 20.2 units and molecular mass of oxygen is 32.0 units. Please read the question once again. A vessel contains two non-reactive gases, neon monatomic and oxygen diatomic. The ratio of their partial pressures is 3:1. Estimate the ratio of 1. Number of molecules in both the gases, and part 2, mass density of neon and oxygen in the vessel. Given the values of atomic mass of neon is 20.2 units and molecular mass of oxygen is 32 units. Given P1 into V is equal to mu1 into RT. This is the gas equation, ideal gas equation. And P2 into V is equal to mu2 into RT. Therefore, dividing one by the other, P1 by P2, we get mu1 by mu2. That is equal to 3 by 2. That is given the ratio as P1 by P2 as 3 by 2. It is in question number 4. Into, that is mu1 by mu2 will be also equal to 3 by 2. By definition, mu1 is equal to n1 by n2 and mu2 is equal to n2 by Na. Na is the Avogadro number. Therefore, n1 by n2 equals mu1 by mu2 equal to 3 by 2. We have calculated in the previous step. We can also write mu1 is equal to m1, small m1 divided by capital M1 and mu2 is equal to small m2 by capital M2. Therefore, if ρ1 and ρ2 are mass densities of 1 and 2 respectively, then we have ρ1 by ρ2 is equal to m1 by v divided by m2 by v. That is equal to m1 by m2. That is equal to mu1 by mu2 into m1 by m2, but that is substituting for these values and rearranging. Please do it step by step. Therefore, we know mu1 by mu2 is 3 by 2 and m1 is given as 20.2 and m2, that of oxygen, is 32. We get the answer as 0.947. Next question. A flask contains argon and chlorine in the ratio 2:1. The temperature of mixture is 27 degrees Celsius. Obtain the ratio of average kinetic energy per molecule and RMS value of the molecules of the two gases. RMS speed. Atomic mass of argon is equal to 39.9 units and molecular mass of chlorine is 70.9. So first we have to find out the kinetic energy per molecule, and in the second part we have to find the RMS speed. Since argon and chlorine both have the same temperature in the flask, the ratio of average kinetic energy per molecule of the two gases is 1:1 only. Part 2. Now, half in m into Vrms square is the average kinetic mv square. Half mv square is the basic formula for kinetic energy. That is the average kinetic energy per molecule. Therefore, that is equal to 3 by 2 into kb into T. This is from law of equipartition of energy. Therefore, Vrms for argon divided by Vrms square of chlorine equals mass of chlorine to mass of argon. That is equal to molar mass of chlorine to molar mass of argon. That is given as 70.9 and 39.9. That is equal to 1.77. Here capital M denotes the molecular mass of gas. For argon, a molecule is just an atom of argon. Therefore, taking square root of both the sides, we get Vrms to Vrms for argon and chlorine respectively. The ratio is 1.33. Next question. The uranium has two isotopes of masses 235 and 238 units. If both are present in uranium hexafluoride gas, which would have the larger average speed? If the atomic mass of fluorine is 19 units, estimate the percentage difference in speeds of at any temperature. Please read the question again and note down the given values. Answer. At a fixed temperature, the average energy is half mv square, which is constant. So, smaller the mass of molecule, faster will be the speed. The ratio of speeds is inversely proportional to the square root of two masses. The masses given are 349 and 352. Therefore, velocity of 349 to velocity at 352 is square root of, because of inverse proportionality, 352 divided by 349. That is equal to 1.0044. Hence, the difference delta V by V is 0.44. Next question. Question number 7. When a molecule or an elastic ball hits a massive wall, it rebounds with the same speed. When a ball hits the massive bat held firmly, the same thing happens. So he is drawing comparison with the molecule and the cricket bat and ball. However, when the bat is moving towards the ball rebounds with a different speed. Does the ball move faster or slower? When the gas in a cylinder is compressed by pushing a piston, its temperature rises. Guess at X and explain this term in kinetic theory using above. What happens when compressed gas pushes the piston out and expands? What would you observe? And part D is Sachin Tendulkar used a heavy cricket bat while playing. Did it help him in any way? So we have to give the scientific reason as to what happened when Sachin Tendulkar used a heavy bat. So let us answer. Let the speed of ball be u relative to the wicket behind the bat. If the bat is moving towards the ball with a speed v relative to the wicket, then the relative speed of the ball to bat is v plus u towards the bat. When the ball rebounds after hitting the massive bat, its speed relative bat is increased by u, that is v plus u, moving away from the bat in the opposite direction. So the relative to the wicket, the speed of rebounding ball is capital V plus u, that is equal to 2v plus u. that is moving away from the wicket. So the ball speeds up after collision with the bat. The rebound speed will be less than u if the bat is not massive. For a molecule, this would imply an increase in temperature. So in case of molecule, the temperature increases. Similarly, we can answer part B, C and D in respect of a gas cylinder based on the answer to A. Here, note down the piston is same as bat, cylinder is wicket and molecule is the ball. This is the analogy between cricket and the gas cylinder, cricket bat and the cylinder. So question 8. A cylinder of fixed capacity 44.8 liter contains a helium gas at STP. What is the amount of heat needed to raise the temperature of the gas in cylinder by 15 degrees Celsius? Assume the value of R to be 8.31 joules per mole per Kelvin. The cylinder in this example contains 2 mole of helium. Further, since helium is monatomic, it is predicted that Cv is equal to 3 by 2 into R and Cp is 3 by 2 into R plus R, that is equal to 5 by 2. This we have seen it in the previous slides. So since the volume of cylinder is fixed, the heat required is determined by Cv. So volume is fixed means volume is constant. It is Cv. Therefore, the heat required is equal to number of moles into molar specific heat into rise in temperature. That is equal to 2 into molar specific heat 1.5 into R into rise in temperature is 15 degrees Celsius. That is given. That is equal to 45 R. Therefore, that is equal to 45 into R value is 8.31. That is equal to 374 joules. Now we will take up 1 mark question. Quickly, write two conditions when real gases obey the ideal gas equations. That is, PV is equal to N into RT, where N is the number of mole. Therefore, answer, what happens that one condition is low pressure. The ideal gas is applicable only when low pressure and high temperature. If the number of molecules in a container is doubled, what will be the effect of RMS speed of molecules? There is no effect. Draw the graph between P and 1 over V, that is pressure, and 1 over reciprocal of volume for a perfect gas at constant temperature and pressure. Constant temperature. The figure is shown here. P is y-axis, 1 by V is x-axis. Name the factors on which the degree of freedom has gas depends. Therefore, answer, atmosity and temperature. What is the volume of a gas at absolute zero temperature? Answer is 0. That is, the volume of gas at absolute zero of temperature is 0. How much volume does 1 mole of gas occupy at STP? Answer is 22.4 liters. This is the Avogadro's experiment. What is an ideal gas? A gas in which intermolecular forces are absent. The absolute temperature of a gas is increased 3 times. What is the effect on the root RMS velocity of the molecule? Answer is it increases. So when the temperature is increased, the RMS value increases. What is the kinetic energy per unit volume of a gas whose pressure is P? So it is 3P by 2. A container has equal number of molecules of hydrogen and carbon dioxide. If a fine hole is made in the container, then which of the two gases shall leak out rapidly? Hydrogen. RMS speed is greater. What is the mean translational kinetic energy of a perfect gas molecule at temperature T? Answer is 3 by 2 RT. Why it is not possible to increase the temperature of a gas while keeping its volume and pressure constant? Because P is equal to 1 by 3 m over V into K into T, and P and V are constant, then T is also constant. Short questions and answers of 2 marks. When an automobile travels from a long distance, the air pressure in the tire increases. Give the reason. Work done is against friction, and which is converted into heat, and therefore the temperature rises. We know that PV is equal to N into RT. As volume of the tire is constant, P is proportional to T. Therefore, the pressure also increases. A gas storage tank has a small leak. The pressure in the tank drops quickly if the gas is hydrogen than when it is oxygen. Why? Answer. Rate of diffusion of a gas is inversely proportional to the square root of the density. So the hydrogen leaks out more rapidly. Why the land has higher temperature than the ocean during day, but a lower temperature at night? This is because of specific heat of water, which is more than the land. Therefore, for a given heat change in temperature, land is more than the ocean. The root mean square RMS speed of oxygen molecule at certain temperature T is V. If the temperature is doubled, the oxygen gas dissociates into atomic oxygen. What is the speed of atomic oxygen? We know that the formula, the specific heat C is given by square root of 3 RT divided by N, which is equal to V. That is equal to, therefore, when the temperature is doubled, that is we made T to T 2T, then C dash is equal to 3 into 2 RT divided by M by 2. That is equal to 2 into square root of 3 RT divided by N. Therefore, C is equal to 2C dash. Two vessels of the same volume are filled with the same gas at same temperature. If the pressure of the gas in these vessels is in the ratio 1:2, then state 1. The ratio of RMS speed at molecules. Part 2. The ratio of the number of molecules. We know that C is proportional to square root of T. And part 2 is P1 is equal to 1 by 3 mn1 into C square divided by V. And P2 is equal to 1 by 3 mn2 into C square divided by V. Therefore, P1 by P2 is equal to N1 by N2, that is equal to half. Question number 18. Why gases at high pressure and low temperature show large deviation from ideal gas behavior? When temperature is low and pressure is high, intermolecular forces become appreciable. Thus, the volume occupied by molecules is not negligibly small as compared to volume of the gas. A gas is filled in a cylinder fitted with a piston at a definite temperature and pressure. Why the pressure of the gas decreases when the piston is pulled out? Answer: when the piston is pulled out, the volume of the gas increases. Now loses the number of molecules colliding against the wall of the container per unit area decreases. Hence, the pressure decreases. With this, we come to the end of chapter number 13, that is Kinetic Theory. Next lecture will be on oscillations, which is a part of chapter number 14. Till then, goodbye.